Hi all, welcome to the Riot Lunch and Learn series, the place where we spotlight Riot sponsors and partners. My name is Jen Morgan and I'm the Virginia program lead for Riot. Just a couple of quick reminders before we get started. This event is being recorded and will be posted to Riot's YouTube channel and uploaded to the meetup page where you registered for this event. If you have any questions throughout the presentation, please place them in the chat. We will be monitoring the chat and we'll read the questions aloud at the end of the presentation. Questions are read aloud for those watching the presentation at a later date. Finally, please keep yourself muted throughout the presentation to help mitigate background noise. Today, we have Vipin from Transphorm to discuss high voltage GaN transistors advantages in power supplies, inverters, and chargers. I'll turn it over to you, Vipin.
All right. Thank you, Jennifer. I hope you all can hear me well. So in terms of presentation and the topics that I will cover today, I'll go over a brief overview of what Transphorm is, compare GaN with other type of transistors, applications of GaN in 30 to 330 watts, and then over 300 watts, look at some advantages of GaN in power factor correction, and then the solutions that are available from GaN, from Transphorm GaN today, okay? I expect that from this presentation, you would walk away with understanding that Transphorm has a full vertical integration of all the major critical steps of the production of GaN. Dynamic characteristics of the GaN are distinctly better as compared to other type of transistors. Transphorm D-mode GaN, which is also called as d-GaN, is one of the most robust GaN technologies in the industry among all other GaN technologies. The thermal coefficient of the d-GaN are significantly better. And then the third quadrant behavior of d-GaN, which the technical depth when we go into later on, you'll see, has a specific benefits within the totem-pole PFC type of applications. And then the d-GaN is very well accepted in consumer and industrial applications as of now, and is about to enter into automotive applications. So those are the key salient points that you will walk away from my presentation today. Let's dig deeper into that. Transphorm. So basically, we are a NASDAQ listed company. d-GaN is our ticker symbol. We have been around since 2007. And we have more than 100 employees. Our headquarters are in Goleta, which is near Los Angeles in California. And our 2022 financial year revenues were $24.1 million. This shows 12.7 in 2021. So this needs update, but 2022 financial year revenue were $24.1 million, which ended in March of 2023, actually. We are today in all these different sectors, and I will talk a little bit more detailed about that. We are strategic partners with some of the top semiconductor players and customers, as you can see over here. So in terms of our value chain, we are we design our own devices. So our low voltage devices are it's a depletion mode high voltage GaN device paired with a low voltage MOSFET in a cascade fashion. Our EPI technology and manufacturing is in-house. We have two locations, one in Japan, one in California, where we have our own MOCVD reactors to make our own GaN EPI. The wafer fabrication is done with our in our joint venture fab in Japan. So we fully control these critical steps of production. And then the packaging is done in various locations around the world. A lot of it is in Philippines today. And we control the full aspects of even the packaging process with our own people physically being there. We are very heavily focused in terms of application support and application resources that we deploy. A lot of them are in California. Some of them are in Asia, specifically in Shenzhen and other places. And then we are going after many different end market applications that we will see in the following slide. If you look in terms of the market positioning of the GaN, GaN really shines, this gray spot that you see over here. GaN really shines when the frequencies are high. And it goes back to the dynamic parameter statement that I make at the beginning of the presentation is that because of the structure of the GaN devices, the dynamic characteristics are very, very good as compared to standard silicon devices or even silicon carbide devices. What that means is that when you switch these devices at higher frequencies, they have lower losses compared to other technologies. And so GaN devices allow increase in frequency, and that means basically increase in power density of the system. So in terms of the markets today, you can think of GaN in 4 different markets. So low power is mostly discrete. So think of like a cell phone charger, laptop adapters, PCs, LCD monitors. These are 45 to 300 watts, and a lot of them use discrete devices. There is a trend for use system in package, meaning you have a controller plus switch in the same, and we do have some partners who are developing those type of devices, whereby we have 25 to 140 watt range of power from us and some of our competition at the same time, and that's where GaN is very well suited. If you look at the mid power range, like 300 watt to 1.5 kilowatt, again, it goes into some high power consumer application, but a lot of it is about solar microinverter or 2-wheeler, 3-wheeler chargers in Asia. And then as you go higher power, 1.5 kilowatt plus, here you're talking about data center power supply, industrial UPS, EV charging, and electric vehicle, especially like OBC and traction inverters that are coming up now. So in terms of the product portfolio, I've not walked you through every aspect of this eye chart. This will be part of the presentation slide that you will get later on. But top row is about the packages, and the row on this first column is about the RDS-on, typical RDS-on at 25 degrees centigrade. And what you see is the part numbers for those specific packages. So we have a broad range of industry standard packages that are, TO247, TOL, D-square, and TO220, PQFN, and so forth. We have automotive grade packages for almost 5 years now. And then we also have a 900 volt industrial grade device in production today. So all of these devices are in production today. Broad range of products. If you compare GaN with other technologies, okay, I need to make this away. So if you compare GaN with other technologies, for 40 to 200 volts, obviously this is the low voltage GaN space, and this is EPC GaN system in a science or the leaders in that space. We don't participate below 600 volt. If you look the 600 volt, this is a 650 volt or 600 volt line of product in the middle. And here you can see the field is very, very crowded with not only GaN, but also silicon carbide and standard silicon MOSFETs. Obviously, Transphorm is one of those, and we will talk about other competitive differences later on. As you go more than 750 volts, I think we have only one product in 900 volt, but this is a space where silicon carbide really shines, and you have all the silicon carbide players listed on the far right over here. This chart goes a little bit into the frequency, which is also equivalent to, say, power density, as well as voltage. So if you look the frequency versus voltage graph, on the low voltage and low frequency, you have basically a power MOSFET area, silicon power MOSFET, okay? As you go into, say, medium voltage range, which is 400 to 600 volt or 400 to 900 volt, here you see there's a lot of overlap of a lot of different technologies, and GaN really shines over here. And also, as you go higher in frequency, GaN really starts to be the only technology available because of the dynamic performance behaviors of GaN technologies. On the far right, as you go very high voltages, it's a space for silicon carbide for the most part. And in some spaces, you might have IGBTs at 1200 volt, for example. But most of it is silicon carbide, especially as you go higher in frequency, silicon carbide really takes the front space there. If we look the segmentation of GaN versus SiC based on the operating voltages, so x-axis here is the operating voltages, I think below 200 volt, you see all these applications, and that's where the GaN transistors are really shining today. And this chart is only comparing GaN and SiC to put things in perspective, okay? Between 600 volts and 900 volts, again, it's a crowded space, and there is a silicon carbide and GaN, all types of SiC and all types of GaN in that space. As you go above 1.2 kilovolt, it is all about silicon carbide in that space. This chart compares GaN with the rest of the other technologies. So what you see in the middle is the Transphorm GaN FET, right? So let's talk about that first. Is best in class RDS-on thermal behavior. So the changes in RDS-on with thermal is best in class for Transphorm GaN. Transphorm GaN can be used with the standard gate drivers because, as I mentioned in the right beginning, we have a cascade structure, meaning the input stage of our device is a silicon low voltage MOSFET. So that means you can use the standard gate drivers, right? We have the best in class third quadrant behavior because our devices use normally off GaN HAMP. That normally on GaN HAMP is actually conducting in the third quadrant. Third quadrant means when your source voltage is high, your drain voltage is low, and the gate is off. And that's the third quadrant behavior. And then the proven reliability in low and high power. So we have more than 100 billion hours of field data of our device operating, and we have shown the proven reliability there. We have both industrial grade and automotive grade products. 650 and 900 volt in production, 1200 volt is upcoming. So very well footprint when it comes to the high voltage GaN technology from Transphorm. We have gone 5 generations of products to, as we speak. And so long history and long footprint both at the same time. If you compare Transphorm GaN with E-mode GaN, I think number one disadvantage that you would face is that the RDS-on temperature coefficient of E-mode goes up. At least by a factor of 10. On top of the RDS-on temperature coefficient, the dynamic RDS-on also kicks in E mode significantly, especially if you have a significant negative drive in a hard switching topology. That could have as much as 50% more RDS-on contribution to your stated RDS-on contribution at high temperatures. On the other hand, in the Transphorm GaN devices, the RDS-on that we specify in the datasheet includes the dynamic RDS-on component to it. And that's a very, very significant difference compared to E-mode GaN, which is most of them only report static RDS-on while provide the glimpse of how to check the dynamic RDS-on. And in this paper that you see at the bottom of the slide gives you the point that I'm talking about, the RDS-on behaviors. In the E-mode GaN, the gate structure is exposed because it's normally off GaN, so the gate structure is directly driven by external drivers. And so you have a lot of disadvantages. Number one is that the voltage thresholds are low. So it's only plus minus 6 volt capability. So not only that, that plus minus 6 volt adds other complexity, but it is not as robust as other transistor technologies that we are used to using. On top of that, the gate thresholds are low. So you need to have a negative drive to make sure that the devices turns off. So that goes to the next point, which is you need special gate drivers for that. So special gate drivers as well as robustness associated with gate are both a big disadvantage when it comes to E-mode GaN devices. When you look at the E-mode devices, I think their field reliabilities are for the most part coming from the low power applications, while our field reliability data is a mix of both low power and high power. I am not reading any chats over here, so if there's anything specific in the chat, please speak it out over here and let me know. Also, I think the only thing I can say about GaN is that they have a superior performance over the silicon transistor technologies. Okay. IC GaN usually refers to components from power integration and Navitas, which are usually driver plus switch. And the one key thing about that is that usually they have specialized packages because the driver is included inside. So you lose out on the packaging part of it also. They're also not very optimal when it comes to high power applications, because high power applications demand a lot of in-application optimization, okay? Also, poor switching control, because the gate driver is inside, you don't have ability to change the drive speed or switching speeds at all. When you compare that with silicon MOSFETs, I think the number one disadvantage of silicon MOSFET versus transform GaN would be switching losses are going to be significantly higher. And of course, it cannot deliver you low power density because of this hard, poor dynamic performance. You cannot switch higher and you need more space. But silicon MOSFETs have a long history, and so they are the incumbent, very well proven. When you look at the silicon carbide comparison with transform GaN, I think silicon carbide has the benefits in terms of the thermal behavior of the RDS(on). Probably it's one of the best technologies out there. Also, silicon carbide is available in 1.7 kilovolt and plus type of technologies, voltages. But silicon carbide, as we know, is a higher substrate cost, higher manufacturing cost, more complexities in the manufacturing. That's the main, let's say, hindrance to the growth of silicon carbide. And then in terms of the switching losses, silicon carbide gate structure are very similar to silicon MOSFETs. So they are better than silicon MOSFETs, but not any close to GaN transistors. If you have any questions, please type them in the chat and I will take them up at the end of the presentation. So if you compare E mode, D mode, and drive GaN, like we just looked at in the previous slide, basically, the drive GaN is basically Navita's or power integration type of products. Basically, if you look at that, number one disadvantage is that you might have duplication of gate drivers in some situation because your controller might include gate driver, but the gate driver comes built in, okay? You always require a bias supply for this stage because there is a gate driver in there. And that bias supply has, number one, power consumption. Number two, if you have to meet critical standby power, you cannot easily meet those. And then this is, you cannot add a lot of functionality. You are limited because these two things are packaged in one device. If you look at the controller E mode GaN, for example, okay, in E mode GaN, I think number one issue we talked about in the previous slide was that you need the level shifter because standard gate drivers cannot do it. You need to have a 6-volt maximum protection, and you need new drivers, specialized drivers for those. When you look at the T-GaN, I think number one is simplest to use because any standard gate drivers can drive our T-GaN, number one. Number two, obviously you get higher frequency because higher efficiency because you're able to precisely optimize the drive speed and snubbers around the devices. You don't need much protection on the gate, and you have all the standard MOSFET packages available for that kind of a device. So there's significant advantages over here. If you look at GaN in a PFC application, because of the performance of the GaN in the PFC application, especially the third quadrant conduction that we talked about before, it's very easy to implement a totem-pole PFC. Totem-pole PFC cannot be done with other technologies such as a standard silicon MOSFET because the noise that is introduced by the body diode of the silicon MOSFET will make it impossible to filter it out in the front-end PFC, front-end EMI filters. So that's why totem-pole PFC is kind of enabled by GaN as we speak. And if you compare a totem-pole PFC with an active bridge interleaved PFC, you can see the number of components in the switches are significantly different. So not only that the component count is significantly less, but also in terms of the efficiency, you have 98.5 versus 98.7, so higher efficiency in the totem-pole bridge-less PFC. If you compare a GaN ham with a super junction MOSFET, you would see that the major differences are in the dynamic performances. Especially if you look at the QG and QGD, there's an order of magnitude difference when it comes to dynamic performance. And that dynamic performance basically results into your driving loss, switching losses, and so forth. So again, when it comes to high frequency switching applications, GaN definitely delivers significantly better performance. This is a comparison of GaN with silicon carbide MOSFET. As you can see over here, this is a comparison in an application that goes up to 8 kilowatts of 7.2 kilowatts of power actually. And the light green is the transphorm GaN versus blue is the silicon line. So in terms of the efficiency itself, you have a 0.2% or 0.3% efficiency difference across the board. But if you look from losses perspective, which is shown on the right, you have almost 15 watts of lower losses with the transphorm GaN compared to silicon carbide here. And that is measured actually on a physical unit. These are not simulated or data taken out from a data sheet. If you look at now 30 to 300 watt range, the topologies under 70 watts are very, very simple. You have usually a flyback AC/DC and a single rectification on the output side. This dashed line inside is what we should think about, because you don't need a power factor correction for under 70 watts. So these are some of the examples, and emerging trend that we see today is integrated devices. So Trend is one of our partners, and they have just released an integrated device for 65 watts of power, and they can streamline a lot of component count on the input stage. This is another device that is based on our GaN technology, and as you can see over here, that the component count goes down significantly. So multiple dies are packaged in same. Power integration, Navitas, Trend, or players that plays very, very predominantly in this market. These are the examples of active clamp flyback solutions that we have. This particular controller SG1131 is from our partner Silana, and this is delivering a power density that is 30 watts per cubic inch, as you can see over here. This is a solution based on diode sync AP3306 controller. Again, a power density of more than 30 watts per cubic inch. And all of these are possible because of GaN. With the standard silicon MOSFETs, this would be an impossible, because you would not be able to achieve the right thermal performance that you need for that. This is over 70 watt. As you go over 70 watt, a PFC stage becomes mandatory. And that's why you need two stage topologies. The first stage becomes PFC, second stage DC to DC, and then you need USB-C output on the secondary side. So this is an example of a 90 to 150 watt adapter. And this is based on a solution that we have developed along with Diode Sync. So AP3306 controller with a synchronous rectification on the output stage, and also the USB-C outside. Okay. Keep going further. So this is a data comparison. And as you can see here is that across the board, the efficiency that we are able to deliver in terms of the input voltage across the board is over 90%, and touching 95% in some spaces. So that very high efficiency is the only reason why you're able to squeeze everything into a small package. Without that high efficiency, you cannot squeeze everything into package. These solutions are readily available either through us or through our partners for even productization. They're close to a final industrial solution. If we look over 300 watts, here the fields become really, really complex. A lot of choices, a lot of optimization, a lot of choices of topologies. And what you would see is that between 300 watts to 2 kilowatt, typically you would see EMI filter, PFC, and then a half bridge LLC type of a topology. While as you go more than 500 watts, the theme shifts more towards phase shifted full bridge for the main stage over here. Again, there is no hard and fast line at the 500 watt or so, but the point is that at higher power, full bridge are preferred. At lower power, half bridge are good enough. Whether it's a soft switching topology or a hard switching topology, GaN delivers superior performance in both of those. If you look at the PFC stage that we talked about before. In the PFC stage, if you have a bridge-less PFC, obviously you have a significant improvement in the component count and a significant performance. So half-bridge topologies sometimes require a reverse conduction, which is also called as a third quadrant conduction. And GaN really gives a better performance, especially transform D-mode GaN is superior compared to other E-GaNs in that space. IGBT does not provide any reverse conduction. Silicon MOSFETs have reverse conduction, but a body diode that could have a very poor performance, and QRR related to that. And then the GaN FETs from Transphorm have very, very low QRR, almost negligible, and then much significantly improved rise and fall times, which also has an impact on the dead times that you can program in your half-bridge topologies. This is an example of a 600-watt PFC boost with a half-bridge LLC design for a 48-volt output. As you can see here, is that this is only measuring the DC-DC stage, as you can see. 98% efficiency is possible. Obviously, it goes down as the power goes down, but for an 800-watt system, sorry, 600-watt system, going from 100 watt to 600 watt, you are above 97% across the board. And again, power loss is only at 16 watts total at the full power, which is a significant improvement compared to any of the prevailing technologies. If you look at the details of that at different line voltages, again, it goes a little bit lower at the lower line input voltage, but again, a significant improvement compared to standard prevailing technologies. This is a portable power station stage, 150 watt, or it can go very high power. These are used in battery charger type of applications. And we can basically do, let's say, either our PQFN or through-hole packages from 50 to 300 milliohm devices can deliver different power levels in these different applications here. So for, let's say, up to 250 kilowatt, 150 or 300 milliohm device would be pretty good in the DC to DC stage. From 250 to 750, 150 or 70 milliohm. And then from 750 to 1.25 kilowatt, 50 or 70 milliohm devices can deliver the performance. Same thing if you look in the boost stage, last 3 digits, by the way, these 3 digits represent the RDS on of the device. So a lot of different options for different power levels in that application. Next few slides goes into reference design, and I'll quickly run them so we have a few minutes for questions and answers. Today, we have reference designs. These are high power reference designs for the most part. So 1.2 kilowatt LLC DC to DC stage. If I will provide these slides in the collateral material later on, you could click on the link, go on Transphorm website, and download all of the soft files that you might need. This is a 450 kilohertz based solution. We have a 600 watt solution that is basically running 150 to 250 kilohertz. Then we have a 3.3 kilowatt solution that can go up to 700 volt DC running at 250 kilohertz. And then we have a phase shifted full bridge for electric vehicle, which is running at 200 kilohertz, delivering 3.3 kilowatts. Then if you look, so what you see on the top are reference design, what you see at the bottom are evaluation boards. So reference design meaning they are really designed for a particular end markets, and you can copy and take them to prototype level. While evaluation kits are more for you to play with and get the feel for the performance of the device in the system. So basically we have solutions from 1.2 kilowatt all the way up to 4 kilowatt with the frequency range, let's say somewhere in the range of 65 kilohertz. And then for the last one at 1.2 kilowatt, it's a variable frequency go from 50 to 300 kilohertz. This is the 1.2 kilowatt solution LSC, which I mentioned in the previous slide. Again, a spec efficiency of 97% is possible. Full power, total power losses for a 1.2 kilowatt system is only 50 watts. So the transistors are really delivering the performance. It's based on a 70 milliohm device. So 70 milliohm device can deliver 1.2 kilowatts of power. We have devices that go as low as 15 milliohms. This is a 600 watt solution. Again, very high efficiency. We talked about that before. Switching frequency from 170 to 250 kilohertz variable frequency because it's the LC topology, and it is based on an onsemi 1397 controller. Again, using 3206 device from us. This is a 3.3 kilowatt solution, and you can get all of these soft files and more detailed data from us. This is a full bridge LLC solution, and based on onsemi 1399 controller, going with a switching frequency of up to 250 kilohertz. This is a 3.3 kilowatt phase shifted full bridge for EV applications, basically onboard charger. In terms of the efficiency, as you can see, it touches 98% efficiency at the full power. So delivering the state-of-the-art performance with a 200 kilohertz frequency solution. This is a 4 kilowatt Bridge-Less Totem-Pole PFC. This is based on a microchip DS-PIC solution. And as you can see here, peak efficiency of 99.3%. Majority of the losses that you see are coming from the series inductors and input filters as opposed to power devices. And GaN can enable that high performance. This is a 2.5 kilowatt Bridge-Less Totem-Pole PFC, again based on a digital solution, DS-PIC from microchip, 66 kilohertz, touching 99% efficiency. This is a 4 kilowatt analog. We have discontinued this one, but again, the soft files and the data are available from us. This is a 1.2 kilowatt synchronous buck boost DC to DC converter, basically testing the half bridge solution that we have. Based on 70 milliohm devices, it delivers a transfer efficiency of 98.8% peak at 50 kilohertz. So it's basically taking a DC voltage, presumably coming from PFC stage, and delivering a AC output for a motor or a transformer. This is a 250 watt reference design with a 24 volt output, and using one device in the PFC, two devices in the half bridge LLC, and delivering full 250 watt solution in a very, very compact board. I think I have the data for that. So this is the data. Again, touching the efficiency, overall efficiency, PFC plus LLC, 94.5 at 50% load, and at 100% load, 95.7% total. And a power density of 25 watts per cubic inch. That's the important part, without any fan. This is a 330 watt platform that we have. Again, similar. A power density of 23 watts per cubic inch. Keep in mind that we have not done any significant investment in the capacitor, transistors, or other mechanical design to improve the power density. This is not the best in class power density. You can achieve much higher power density than this with these applications. This is a 240 watt design. Here we have slightly improved in terms of power density, touching almost 30 watts per cubic inch. You can see here the efficiency across the board is over 94%. This is a phase shifted full bridge DC to DC only. And as you can see over here is that if you look the hard switching region and you compare a CFD, which is a fast body diode Infineon CoolMOS versus a TPH transform GaN device, you can see that when the device is hard switching, especially in the low power space, because this is a phase shifted full bridge. So there is some hard switching involved in the low power space. You can see that the efficiency drops significantly. At 1 kilowatt power, you have an efficiency difference of 93% versus 97%. And that is mainly coming because of the body diode contribution from the Infineon device. Transphorm doesn't have the body diode impact, and that's why it can deliver much higher switching frequency. So again, coming back to my last slide summary, I think if I can reiterate, Transphorm controls all important aspects of GaN manufacturing, and that's why we are able to deliver the reliability and the yield that is needed for high reliability applications. Dynamic characteristics of the GaN are distinctly better as compared to all the other technologies. There is a distinct differences between Transphorm GaN and other GaN technologies in terms of robustness, gate drivability, and so forth. The thermal coefficient of d-GaN are better compared to other prevailing GaN technologies. The third quadrant behavior of d-GaN is beneficial in the totem pole and the phase-shifted full bridge topology that we just looked at in the last slide a minute ago. And then the d-GaN is in production, high volume production in consumer industrial applications as of today, and entering in the automotive applications as we speak. So with that, I think we can open the floor for Q&A. Anybody has any questions for me?
Wow, that was fantastic. Thanks so much. We'll now take some questions. If you have any questions, please place them in the chat box and I will read them aloud.
You can unmute everyone now, Jennifer.
Well, I have a couple of quick questions.
Sure.
The first question that I have is how many units of Transphorm has shipped out so far?
So the FET data that we talked about is based on 16 million or so units that we have shipped so far.
Awesome. One of the questions in the chat is where is your market driving? More towards 12,000 plus volts or higher current?
So today, I think the 650 volt market is predominant. 1200 volt is just released, so not yet in its prime. It will eventually be, but 650 is the main today. 1200 volt, I would say, probably still 2 years away from its prime.
Awesome. Another question that I had is where does Transphorm GaN fit best as it's compared to SiC or silicon MOSFETs?
So I think Transphorm GaN definitely is a better cost proposition compared to silicon carbide, like we talked about, and the trajectory of the Transphorm GaN in terms of cost is more promising compared to silicon carbide. Silicon carbide is a mature technology. In terms of the market size, silicon carbide is 10 times bigger than GaN as of today. So has achieved quite a bit of maturity, while GaN is still in infancy stage. So if GaN can deliver the performance of silicon carbide and the trajectory of the cost is better, then definitely GaN has a very big potential. The two main applications that I mentioned where GaN has distinct advantages are totem-pole PFC and phase-shifted full bridge. Also, all the applications that demands higher power density, GaN definitely is better than any of the other technologies.
Another question is, what uptake are you seeing in EV OEMs for onboard charging?
So the trend in the onboard charging is to go higher in frequency. Okay. Today, onboard charging is a mix of silicon super junction and silicon carbide, but there is a limitation to how much frequency that they can raise in the onboard charging. And that's where GaN plays a significant role in enabling future onboard chargers with frequencies of 500 kilohertz or even more, which are impossible to do today with the silicon carbide or silicon MOSFETs.
That's all the questions that I'm seeing, but I'll leave the floor open for another minute. In the meantime, what's the best way for the audience to connect with you?
Good point. My email ID is very simple, vipin.bothra@transphormusa.com. Maybe I can type on a screen or you can chat to everyone, Jennifer.
Yeah, absolutely. In the meantime, there's one other question. Is, do you think there's an aftermarket opportunity for EVs?
I don't see that as of today because there is a lot of qualification and industrialization has to be done by OEMs before it goes into aftermarket. But two-wheeler and three-wheeler, which are similar to aftermarket, are really thriving with GaN today. So as far as the four-wheeler EVs are concerned, I think there is still some time before it can be adopted into aftermarket because industry has to go through a lot of learning before that.
Any final questions? Well, if anybody has any other questions, please feel free to reach out. Thanks again for such a wonderful presentation. As a reminder, Riot hosts Lunch and Learns weekly on Wednesdays at 1 p.m. on Eastern Time. You can find a list of all of our upcoming Lunch and Learns on the meetup pages where you registered for this event. This event was recorded and will be posted to Riot's YouTube channel and the meetup pages where you also registered for this event. Thank you all for joining us today. I hope everyone had a great time and enjoys the rest of their day. And thank you so much. Bye.
Thanks, everyone. Bye-bye.